So I'm going to start with just a few, facts about the ionosphere, which may make some of the squirrely behavior we seem normal, and I think you'll understand when you talk about that. First of all, let's talk about what the atmosphere is. The atmosphere is an extremely wide-ranging variety of, or I should say, pressure of gases. Uh, what what we want to probably show is how gossamer the upper ionosphere is. And if anything that's that non-existent, shall we say, it's not surprising that we have a lot of unusual things happening. So the density of the atmosphere at the upper extreme of the F layer is about 1/4 of the density of air at sea level. That in itself can explain about 99% of what we experience as far as weird propagation. So in other words, there isn't much up there. The relative composition of the atmosphere is fairly constant, however, regardless of altitude. It's pretty well homogenized up to a limit. So uh, we'll talk mainly about nitrogen because that's the main ingredient of air, and that's the main source of ions that we're going to be working with. Um, Now we have obviously you have other gases here, but the impression a lot of people have, well, all the lighter gases like helium and neon are going to float to the upper ion, float above all the rest of the ionosphere or rest of the atmosphere. And that'd be wonderful if they did. If we had a nice solid layer of argon up there, which is very easy to ionize, we'd have almost a mirror type reflection up there. But it doesn't work that way. Everything's kind of homogenized together to a wide degree there. So as it turns out, the noble gases really have very little to do with what we have experienced as far as radio propagation. It's mainly the main ingredients, which are primarily nitrogen and oxygen. Now, to give things a little perspective here, the ionosphere really, as far as radio is concerned, really should be called the electrosphere, and we'll explain that. So a couple of little numbers here. A proton has approximately 2,000 times the mass of an electron. However, the magnitude of the charge is the same. Uh, Moving along in this same vein, nitrogen has an atomic number of 7, but it usually comes in the form of an N2 molecule. So we basically have an atomic number of 14. When ionized, it's most frequently an N2 plus ion. There are other ionization states and many excitation states, but primarily the simplest is going to be the N2 ion. Now, the chemistry involved in the ionization can be a lot more complicated than just slapping an electron off and whatever's left is an ion. There's sometimes some intermediate states there, but we'll just go from the beginning to the end and skip all the stuff in the middle. So as far as the orders of magnitude, so an N2 molecule ion has about 28,000 times the mass of an electron. But remember that the charge of a proton is exactly the same as electron, except the direction is different. So this means for the same electric field strength, the electron will accelerate 28,000 times as fast as a nitrogen 2 ion. And this means that free electrons, or at least very cheap electrons, are the active ingredient in the ionospheric radio propagation. Now, you might all have a question about, well, protons do have a charge to them, so do we ever directly manipulate the protons with radio? Well, yeah, with 28,000 times the power necessary to do that. We'll talk about some of the nonlinear effects that have when we actually do excite some of the ions or wobble them around in addition to the electrons. The primary ionizing ingredient is UV radiation from the sun. It's not the only process, but that's the main one that's actually useful for us. X-rays can also give us a lot of ionization, but they do usually not too useful because they usually penetrate to the down to the D layer and cause more absorption. So we have a kind of a balancing act as far as propagation is concerned. Let's see. Yeah, UVA radiation from the sun is primary cause of ionization of air molecules of any species. Okay, so when an electron gets slapped off ions, what prevents the electrons from repelling each other and blorping off into space? This is an open question. Who wants to answer this one? Okay, well, we know electrons repel each other. So if we have a bunch of electrons in a cloud or whatever, we would expect them to go wandering off into space and be absolutely worthless for us. However, what keeps the ions in space is, or keeps the electrons in nearby, is when they get slapped off the ion is now positively charged and it wants to attract the electron back into it. So we have a situation where we have basically electrons in a very long leash, but they are on a leash. They never actually get too far away from the ions from which they got ripped off. And this has been proven with in situ measurements from sounding rockets that shows that the ion density profile very closely matches the electron density profile, which basically says when we rip an electron off an ion, it doesn't move very far. It pretty much stays in the same vicinity. So this is what caused the electrons to form in nice, neat layers that are actually useful for us. Now, one thing we do not want from the sun is a lot of heavy charged particles, because heavily charged particles create a lot of turbulence. It's a very mechanical way of looking at it, but that's really what happens. If you want a nice surface of a lake, which is highly reflective, and you throw a bunch of gravel in it, you're going to have a bunch of turbulence and ripples and everything else, which is not going to do you much good. So you want a pretty well-defined layer of electrons that are going to be highly mobile, but you want them in a layer. You don't want them in clumps and random clouds of electrons, which are not really good for radio propagation. On another note there, that we have this phenomenon called electron precipitation, which we actually get well, I need to preface this that in general, the overall charge of the Earth on a net charge is usually pretty neutral. However, we get localized and temporary large numbers of electrons that occur that precipitate out of an auroral phenomenon. So we actually have a highly positive or highly negative charge on the surface for a while. I was really amazed when I was working at High Pass Observatory. We actually had a plain old ordinary electroscope, which is just basically a jar with a couple of pith balls in it, and you can measure static charges. And after visible aurora, we would always see these pith balls separate from each other. So we obviously were collecting some of these extra electrons, which eventually dissipated. But it's probably a good thing that this does happen. Otherwise, we'd have a highly statically charged Earth, which would probably not real beneficial to life. So the process of ionosphere reflection is really, I should say that's the end result looks like reflection, but it really isn't. We actually have a refraction, and even getting more detail, what we have is actually re-radiation. The electric field of a radio wave going through charge carriers like electrons accelerates the electrons, and then the electrons, by virtue of their being accelerating, re-emit electromagnetic waves. So it's kind of a fully reciprocal process that we have here. So we always have the question of, which came first, the chicken or the egg? And I don't know if we ever really answer that, because electromagnetic waves accelerate electrons, and electrons accelerating electrons create electromagnetic waves. We talked a little bit about some of the different propagation modes here. And this is quite similar to I should say what commonly happens in amateur radio. We can't always define what our propagation path is. We have F-layer propagation, as we have here, our standard, what we call our standard HF propagation. We have sporadic E propagation. We have non-sporadic E propagation. Everybody talks about sporadic E, but there's also some non-sporadic E, which is a little particularly uncommon in parts of the world. We have chordal hop propagation, which usually happens at very low frequencies, where you have multiple hops off the ionosphere. Did I see a question? So a hand go up. Okay. We can have multiple hops off the ionosphere without intermediate hops off the ground. And this particularly is on the dark side of the Earth. Particularly at lower frequency, 160 meters and 80 meters, you're quite likely to see chordal hop propagation. And this mode has extremely low losses. And matter of fact, there's been some evidence that we may actually get some gain of the radio signal on these modes here. What by means of what's called parametric amplification. Now, all the ingredients necessary for parametric amplification do occur in the wild, but having them all occur at the same time is probably very rare. So it's probably as rare as long delayed echoes, and I've given a whole talk on those before. How many, by the way, how many here have actually experienced long delayed echoes on maybe 40 or 20 meters? Nobody. Okay. Yes. Oh, a little bit, perhaps. Yeah. There's some plausible theories for that happening, and we will go into that in a great deal of detail here. But this slide here basically shows that we have not only many different modes of propagation, but we have mixed modes. So, for example, you could have something that a signal goes up to sporadic E for a while, and then comes back to Earth, and then bounces up, and then comes off to normal F layer, or any combination thereof. We can have backscatter propagation, forward scatter propagation. Just about any combination thereof. So, but going back to the fundamentals here of remembering that it's the electrons that actually do the work for us. It's the electrons are the active ingredients in 99% of the propagation we experience. Geez, right here. We can't ignore the sun. Most of us agree that if we didn't have the sun, amateur radio would be much less enjoyable. So we do have certain things that we can talk about the sun. Now, I wrote an article in QST a while back, said don't blame the sun too much. Basically, the sun is a prime mover of everything we have, but it can be quite delayed. So looking at the real-time ionosons is actually going to give us a lot more local information of what we're normally going to experience. Here's some just basically numbers that we're talking about, solar flux and sunspots, and most of us are pretty familiar with that. One of the misconceptions about sunspots is that sunspots themselves do not create the UV that we need. They are basically indicators of the UV that's already being transmitted on the sun. And part of the reason we know that is when we have a lot of sunspots, even if they aren't aimed at us, quote unquote, they still do us a lot of good. So even if they're right on the limb of the sun there, if we have a lot of sunspots, generally propagation will be good. So they're really indicators of what's happening in the sun on a much larger scale there. Now, again, we don't want coronal mass ejections coming from the sun because these highly charged particles, often protons, those aren't the only species we have, but heavy charged particles do not do the ionosphere any good for normal propagation. So we want a lot of UV radiation. We want a kind of a uniform baking of the Earth, but we don't want a huge blasts of coronal protons and other species there. The difference between UV radiation, which is electromagnetic radiation, it gets from the sun to us in about 8 minutes. Whereas coronal mass ejections can actually take several days. So the electromagnetic waves are very fast. Charged particles are much, much slower. So we have enough time to duck when we have a coronal mass ejection. Difference between the K and A index is really how it's averaged. K index is computed once every 3 hours, 8 times a day, and the values can range from 0 to 9, with 0 being inactive and 9 representing an extreme severe storm. So we have kind of a logarithmic scale here for that. The A index is more linear and is computed from the 8 previous K index values. And we have just a 0 to a 7 is quiet, 8 to 15 unsettled, 16 to 29 active, 39 to 49 is a minor storm, 15 is the 99 a major storm, and 100 to 400 is a severe storm, which basically is going to result in a radio blackout. Now, a lot of what some of us are familiar with, or we're fond of saying in Alaska that a radio blackout is not an event, it's a state of being. And that's pretty well true if you've done much hamming in interior Alaska. And now it's different universe once we get below the auroral oval in what we call the tropics of Alaska. So Anchorage area and a lot of the lower parts of Alaska, they don't have the same phenomenon that we have up in Fairbanks, where we can have just basically no radio propagation for months at a time. So we learned to live with it. Here's a little bit of interaction. Now, this is highly simplified, as everything in this talk is. There's just only so much we can cover here. This is entitled Solar Storms and Why We Care, and it shows basically the magnetosphere that surrounds the Earth and is energized by the sun. We have basically the magnetic field of the Earth is the opposite direction of the sun. It's like two bar magnets you have. So we have very close connection between the magnetic field of the Earth and the magnetic field of the sun. And this changes periodically, perhaps every couple of hundred years. You have a total reversal of both the solar magnetic field and the Earth. Usually in the time that it's actually reversing, it can actually split up into multiple poles. So we don't have just a single north and a south pole. We can have all sorts of weird things happening. And historical ships records with magnetic compasses show there were some errors there in relatively recent history where everything went just totally bonkers for a couple of years. So magnetic compasses were pretty much useless for a period of time during the splitting up of the magnetic field and the eventual recombining. I understand we are kind of at the beginning of a magnetic pole reversal, even as we speak. So it could take decades for it actually to finally flip over there. So let's see, second paragraph here. Yeah, when the BZ, and that's the Z-axis magnetic field is south, that is the opposite of the Earth's magnetic field. The two fields link up. So just like a bar magnet, they are going to want to connect to each other. And again, it's extremely oversimplified, but to give you the idea that we have a very tight coupling, magnetic coupling to the Earth. The magnetosphere also protects us. So when you have these coronal mass ejections, so we don't fry ourselves to a crisp, these heavy particles are propagated around the Earth following this magneto tail here, and plasma sheets and all sorts of ingredients here. So again, this is a highly simplified chart here. There's a whole lot more different layers here, but this basically gives you the idea of what the solar wind is. The sun's coming this way, and the magnetic field do protect the sun to a large degree. During these solar ejections, though, or auroral activity, whenever you have auroral activity, there is going to be some electron precipitation, which is electrons that come down the magnetic field lines and eventually end up here on Earth. That in itself probably doesn't have a whole lot to do with the radio propagation we observe, but it is a very interesting phenomenon. It was not too long ago I actually heard the term electron precipitation. So that's kind of a strange term. Does that really exist? Well, yes, indeed it does. Let's see what we got here. Okay, ionosons, your window to the ionosphere. And again, I wrote in my article, give me an X, don't blame the sun too much. The ionoson is a really good tool for knowing what's happening. Now, the ionoson network is no longer as prominent as it used to be. It's been kind of crippled in recent years, but there's still a lot of great information you get from that. So we're going to talk about how to interpret an ionogram. And even if I go to historical ones, look how it's supposed to look, it gives you a lot of insight there. An ionospheric sounder uses basic radar techniques to detect electron density in the ionosphere as a function of height. Each component of solar emissions tends to be deposited at a particular altitude or range of altitudes. Peaks of these layers form between 70 and 300 kilometers altitude, if we include the D, E, and F layers in that order. By the way, we very seldom see a separation between the F1 and F2 layers here. The real separation is which ion is being ionized. So usually the F2 is when you have a lot of oxygen ionized, and F1 is primarily nitrogen. Now, at no time in this discussion do I want to leave with the impression that we have any layer in the ionosphere that's nothing but electrons or nothing but protons or nothing but neutrals. It's a mixture of everything. So when you talk about electron density profile, we're talking about the relative concentration of electrons relative to unionized species. So we don't have We always consider everything as being part of a soup. So it's simply a matter of, how much of a one ingredient we have in the soup and not. One possible exception where we actually do have very large clumps of electrons is sporadic E. And sporadic E is sporadic for a reason, is unlike in F layer ionization, where we have all these ions kind of keeping the electrons on a long leash. Uh, well, there's several sources for sporadic E. One of them is lightning, one of them is wind shear, a couple of other phenomenon, meteor bursts, micrometeors coming in and ionizing that region, and a few other things. Well, the reason sporadic E is so different from F-layer propagation is we no longer have ions holding these in place. We basically have neutrals. So we have the electrons which are attached to a neutral, which now the electrons, since they aren't really attracted to the neutral, they can somewhat embed themselves in neutral particles. But as a general rule, the electrons in sporadic E will repel each other, and that's why it dissipates so rapidly. So there's still a whole lot of that's being done with sporadic E propagation, lots and lots of mysteries of it, which is why ham radio is so fascinating. There's forgot his call sign, but prominent member of the RSGB gave an outstanding talk on just sporadic E. Well, yes, there's also a thing called gravity waves, which are basically we sometimes forget that the ionosphere rides on top of the atmosphere. And as we mentioned, the density of the ionosphere is so much less than the atmosphere that we would say, okay, who has the most, which affects which the most? Well, obviously, since there's so little mass in the ionosphere, that its effect on the lower atmosphere is almost non-existent. Whereas the atmosphere, the breathable atmosphere, or up to the troposphere, has so much more mass to it that it's going to affect the ionosphere much more than that. It's kind of like the principle if you're driving a car, you want the car to have as much mass moving in the same direction as you do, which is going to make you safer. So basically, we got this massive Buick in terms of the atmosphere and this very, very gossamer, almost non-existent ionosphere floating on top of that. I hope these numbers kind of give you an appreciation is the fact that there's so little material up there that we can still have have an effect on radio as profound as it is. Our friends at ISCAT, which is the European huge ionospheric heater, and they do a lot of other things there. They actually calculate the entire mass of the ionosphere of what we're interested in. And the entire mass of the ionosphere that's of interest to radio is about a metric ton, which basically you could compress the whole thing into a tank and put it on a pallet truck and scoot it into your garage. So it's just amazes you. It should amaze you how little material there is, and the fact that it has this much effect on radio. It's quite amazing that so little material can have such a huge effect. Let's talk a little bit about the digisonde itself, which is for many years was the ionospheric sounder. And so what we have here is an actual digisonde transmitter here and the computer control and all that. And it's basically a radar, which is swept from some low frequency to a higher one. There's typical ranges that they sweep over, but everyone is programmed differently depending on the need and your particular location there. And so you can see on the screen here, it does show an ionogram there, and we'll talk about those in much more detail here. Here is one of the digisonde receiving antennas, and usually have 4 of them surrounding the transmitter antennas. Notice this is circularly polarized, and we'll go into that in a great deal here. The reason it's circularly polarized is because there's a phenomenon called X and O propagation. And what's really interesting about X and O propagation, even though it always exists, there's been almost no mention of this in the amateur literature. In December 2010, I wrote an article called "Give Me an X, Give Me an O, What's That Spell Radio?" And I went through an entire search of the ARRL archives, and it was the only mention of X and O propagation in ARRL literature since March of 1940. So with a 70-year gap of no mention of X and O propagation, which I thought was kind of strange, because that's kind of how radio works. But we'll talk about we'll mention that in this ionogram. So what you here have is a typical ionogram. This is taken in Boulder, Colorado, really close to where we're at right now. And we'll talk about some of these features here. And again, the digisign is kind of becoming somewhat extinct, but there are other types of ionosondes out there. Matter of fact, I built a straight Doppler ionoson for when I was working at High Pass Observatory. But anyway, what we have here is we have across the bottom scale here, we have frequencies. And this one particularly scans between basically 1 and 16 megahertz. On this left side, we have the height of reflection, and this is in kilometers. And we have a bunch of other extra information here, but we'll talk about stuff that's actually more relevant to amateur radio propagation here. So what we have here is we're sending a pulse straight up. It's called a vertical incident ionoson. And it looks for a reflection. And as we see here, we have these red traces here, which is probably the more common one. And as we see, as we increase the frequency, the reflection height increases further and further and further, and then goes straight up, which means at that point, the radio propagation is going clear through to outer space. And so that's what we call the critical frequency here. And that critical frequency is what we call we could call it the worst case scenario as far as reflection capabilities are concerned. If you go on the scale on bottom, we have the MUF. And the MUF is maximum usable frequency. And you see that this changes depending on what your launch angle is. So again, with a vertical sounder, this is a worst case scenario. You're going to always have the lowest critical frequency. However, if we look across the scale here, way over the right here, we have at 3,000 kilometers, that's our first hop distance, which basically you're launching the signal straight horizontally. We have our MUF here is 31.3 megahertz. Now, that's obviously not this year. This is back in 2012. We don't have anything like that. Well, we might be getting some of this again as we move to the sunspot cycle, but for many years, we didn't have any MUF anywhere like this. So you see, as we increase or decrease the horizontal, we want to start with, call it the zenith angle. Zenith is the opposite of elevation. So we basically start at the zenith straight up and move downward. So as we move the zenith and we move it downward, we see the MUF increases. As we move down, like for example, 100 kilohertz first hop, we're not quite vertical incident, but we're pretty close to it. Maybe 80 or 80 degrees or so. We're going to have an MUF of pretty close to the critical frequency. So here we have, oops. Hello, what happened here? Oh. There we go. Okay, well, we're going to have frequency which is not much above the critical frequency here. So this chart down here is probably the most usefulness for predicting radio propagation, and most of the predicting software, for example, if you have DX Labs propagation or DX Labs ham radio suite, it does have a lot of propagation prediction, which is pretty much based on this down here. Now, again, the ionoson is not or the digison or ionoson is not a predictor. It doesn't predict directly. It tells you what's actually happening now, which is sometimes a lot more useful than guessing what's going to happen in the future. No matter how much information you have, it can lie a lot. The digison or ionoson does not lie. It tells you what it actually is based on real-time, real reception. Let's see a few other features here. Okay, this black trace here is called the electron density profile. And basically what this does is tells you the relative concentration of electrons. And since this is taken somewhere during the daytime, this peak here, we have a maximum number of electrons here at about 250 kilometers, which is quite typical. And so now something very interesting happens. If you look at where this peak happens, it's also at the same place where the critical frequency occurs. So if you look at this red trace where it goes straight vertically, it'll always coincide with the cusp of this electron density profile. Now, one thing that's very interesting is it's also a dotted line above this frequency. And why is that? That is because from a ground-based ionoson, you cannot probe anything beyond that critical height there. So in order to get this dotted line here, you have to do what's called a topside sounder, which are digisons actually on some satellites. They're kind of few and far between. There never have been a whole lot of these topside sounders, but on special purposes, they will have one up there. And then you can actually get this in real time. The reason this dotted line is this is predicted mathematically. It's not actually measured, where everything below this cusp can be directly measured. Now, here we go with the red and green. What we have here is the X and O propagation. And if you launch a linearly polarized signal into the ionosphere, it splits into two components. One is clockwise circular polarization, and the other one is counterclockwise circular polarization. We showed you that digison antenna here, going back here, has a circularly polarized antenna, so it can discriminate between right-hand and left-hand propagation that's come down. The right-hand propagation, or what we call the ordinary mode, or the O mode, is this red trace here. And the extraordinary mode, which we call the X mode, and we call it the X mode because physicists can't spell, so it is the green trace. Now, depending on how strong your magnetic field is, the divergence of the X and the O mode is going to increase. If you're right on the magnetic equator, for example, if you were to look at a digison from Cajamarca, Peru, the red and green traces will be almost always right on top of each other, which basically means there's no divergence. The closer you get to the poles, the more the X and O are going to diverge. Now, we're only looking here in pretty much two dimensions. We're looking at the height of reflection, which is, again, the critical frequency for the X mode would be slightly higher than it is for the O mode. But this doesn't show you what the divergence is in terms of azimuth, and that can be very, very different. The path, especially when you get up here, the X and O modes can diverge on the azimuth 90 degrees. So you send a signal up there, and somebody in Sweden may hear your X mode, and somebody in Canada might hear your O mode. That's just an example. There could be very extreme differences in there. Let's see. What do we have up here? Can anybody want to guess what this is up here?
Yeah, that's the reflection of the original signal. It took a second trip.
Yeah, second trip, right. I have seen as many as 6 reflections. Now, it doesn't happen very often, but if you see multiple reflections, what does that tell you? Why is that a good thing?
Well, multiple reflections means that the initial reflection was very, very strong.
Well, basically means you have very low absorption.
Yeah, very little delay.
That's right. So, and again, we have very, very tenuous balancing act and make the ionosphere work at all. It's a lot of things have to come into play here. Okay, so what is this? What do you think this is?
Sorry, what are you pointing to?
Oh, right here.
Oh.
Or here.
This is sporadic E propagation. That looks like low of the sunspot cycle on.
Well, sporadic E, oddly enough, does not depend on sunspot cycle that much. It can happen anytime. But one reason we know it's sporadic E because it starts so low. The F layer starts, up here. The E layers usually runs between 60 and 90 kilometers. Now, this is actually relatively high for sporadic E. But the real telling thing is it doesn't change with frequency. It's the same. It's straight horizontal here. So unlike the F layer where you have this critical frequency, sporadic E does not have a critical frequency as such. Now here, again, this is a second reflection of that. And here we see a little trace of a third reflection of sporadic E. Now, sporadic E is only partially reflective, although it can be quite specular, which means mirror-like. You can also have, at the same time, see F layer reflection overhead. And you say, well, how can that happen? If the E layer is reflecting everything down to Earth, how do we get anything through it to go to the F layer? Well, that's because it's only partially reflective. So we have a lot of things working for us and against us here. So let's talk about why there's a particular height where we have a maximum electron density. Now, going back to the source of ionization, uh, again, what's the main source of ionization that we're interested in?
UV from the sun.
Right. Now, at very low altitudes, the density is very high, and we know that the higher the pressure is, the harder it is to ionize something. However, as we go up very high in altitude, there's less stuff to ionize. So we have these two conflicting interests, I guess we could call it. So where this occurs at this maximum electron density is where we have a convergence of having a sufficient number of atoms to be ionized, but it's not so dense that we can't ionize them. So there's a happy medium there. X-rays, again, will penetrate the ionosphere further, and we can get more lower level ionization in the D layer and some of the E layer. So X-rays, again, are good for some things, if you like absorption. But in general, we want UV, primarily UVB, which is near or far ultraviolet. Other sources of ionization, again, for sporadic E are lightning storms, where we have just massive chunks of electrons being precipitated out. Micrometeors, ablation of micrometeors, and we did quite a bit of studying in this using laser optics to actually look for micrometeors coming in and then watching the ionosphere at the same time, and tremendous correlation. Usually during let's see, when I was at high pass, it was the Leonid shower. Yeah, Leonid shower was very prominent there. So we were watching meteors go by all week long and observing the sporadic E increasing. There's also a lot of other phenomenon too that happens to that. Let's see. Oh, yes. Okay. Now let's talk about something really important. Is the difference between real height and virtual height. Now, assuming the ionosphere was just a mirror, we could very well define what the height of reflection is. We assume that the speed of light is speed of light, and we can determine the height very accurately, and there will be no conflict of interest or no ambiguity. However, the ionosphere is not a mirror; it's a constantly changing dielectric constant. Imagine a transmission line where it has a constantly changing velocity of propagation as you move along the transmission line. So what we have here is, rather than a hard reflection at a point here, we have once the radio waves enters the ionosphere, it continually slows down. And it doesn't do this in a very linear fashion because air is a gas and air is compressible, and because we have anything that's compressible makes things very nonlinear. If it were a liquid, it might be something quite different. But anyway, as a radio signal propagates through the ionosphere, it slows down, and so the speed of light changes from very near the speed of light before you enter it, and slows way down, and then reverses direction, and then accelerates again as you come back. So the actual time of flight through the ionosphere is much longer than you would expect for a simple specular reflection of some height. And that's where we have over here, we have the height, and we look at the virtual height and the real height. And the real height is, again, what you would actually have if you were to have a specular reflection here. So anything with an H here is designated height. So we have H prime, and I believe that double prime is actually that tells you the thickness of the ionosphere. It's been a while since I've looked at this one, but you see there's quite a bit of difference here. The virtual height is 233 kilometers, and down here it's down to 199 here in the HF2. So we have a significant difference between the real height and the virtual height, and So that makes things some very, very interesting. Now, most of the time, when we're predicting how far a radio signal is going to be on the first top, we're actually using the virtual height. That's actually going to be more meaningful to us because that's because the radio waves, especially at low angles, spend a lot of time in the ionosphere. Uh, and the geometry is pretty simple on that. If you're looking straight up through, let's say you have a given thickness of ionosphere, and we're shooting straight up, it gets through it and comes right back to it relatively quickly. If you're looking at grazing paths through the ionosphere, it can be thousands of miles long before you ever re-emerge from that. And since it spends so much time in the ionosphere, it's also spending a lot of time being very slow in the ionosphere. So you see a lot of dynamics happening here that attests to the fact that how the ionosphere really works is very uh, shall I say, oversimplified. Presumptuous on anybody would claim to know how the ionosphere works. But anyway, any questions so far, particularly on the ionoson, how to interpret that? Now, there's a lot more information that's useful to physicists. It doesn't really tell us much as radio amateurs. Again, the primary thing that we'll notice is the X and O propagation, which is separated into the green and the green and the red. However, we also have Doppler shift happening. So if we have a just like red and blue shift in intergalactic light, we also can have red and blue shifts of these colors here. I don't have an digisign that shows that very clearly, but we'll sometimes see this red is very purplish, and sometimes the green is very much toward the yellow. And so if you just think of it in terms of red shift and blue shift, you can tell how fast the ionosphere is moving. Now, I built this universe. It was a special purpose Doppler ionoson at High Pass Observatory, which, by the way, was the predecessor to HARP. So this, all it would do is stick on a single frequency. We weren't looking for critical frequencies. What we were doing is basically looking at how fast the ionosphere moves. And after sundown, the ionosphere, well, as a general rule, or I guess it's a pretty fast rule, at nighttime, the ionosphere retreats. It gets thinner from the bottom up. That's why on 80 meters, whatever we say, the band goes long. That's because the ionosphere is thinning out from the bottom up. And that thinning process becomes very rapid. I've seen it with our Doppler moving upwards at 700 meters per second. I mean, that's just screaming. So when it finally retreats, it does it very, very fast. And it expands during the morning hours quite a bit slower, but the receding speed is very, very fast. Now, a couple of things that can cause fading and other weird phenomena as well is, remember, the ionosphere is not flat surface. It can have ripples and waves, and if anybody's ever seen the aurora, we have this curtaining thing happening, which is all highly visible on ionospheric radar. So you can, since you aren't sending a laser beam up there, it's not a death ray, it's a pretty broad beam, usually maybe 25, 30 degrees wide. You're getting reflections from a lot of geographical areas of the ionosphere. So you can sometimes see on a Doppler, you see actually two rotating plots, ones where parts of the ionosphere are moving up and parts are moving down. So it's just like grabbing a carpet and whipping it and having the waves go through there. So some parts will be receding and some will be coming closer. And so this is, it really shows how non-uniform the ionosphere is, except in extremely quiet cases. But it can cause all sorts of things like fading and, so particularly a selective fading where the actual MUF is changing because the launch angle or the reflections from the wrinkled ionosphere occur at different times, and they can either add in phase or out of phase. So you can have some very rapid fading there. Again, we're trying to describe in 2 dimensions. There's actually multiple dimensions, at least 3 dimensions we were talking about there, but we can have some other phenomenon in there, which actually gives us more dimensions, at least to look at magnetically. Let's see, what chart is this here? That one. Got a slide here. Okay, that's sporadic E. Food for thought. Scoot this over here. Yeah, talk a little bit about X and O. I wrote this little blurb here. I'll probably need to revise this, but for about a century, there's been a conspiracy of silence in amateur circles about a couple of things known as X and O propagation, which is just clearly demonstrated. It's really surprising since X mode and O mode propagation modes have been known for at least 60 years and are fully acknowledged by just about every communications professional. So this is only us hams who have been ignorant of this. X and O propagation was actually known back in early 1800s. Faraday rotation is a result of this. The optics people have long known about X and O mode propagation through magnetized solids and that sort of thing. And by the way, it is the magnetic field that does cause this to happen. If we had no Earth's magnetic field, we wouldn't have such things as X and O propagation. But because we do have the Earth's magnetic field, whether you're going across the field or perpendicular or parallel to the field, the propagation would be very, very different. And again, the O mode is the ordinary mode, which is clockwise in the northern hemisphere, and in the southern magnetic hemisphere, these definitions are changed. Now, there's not 100% agreement between physicists and electrical engineers on what we define as circular polarization, or what we define as a sense of circular polarization. The safest way to define it is looking in the direction of the wave is propagating. So if you have a right-hand screw, that's the direction it's going to change. So the wave going away from you would determine the polarization of the wave, or rather the sense of the wave. Again, this is not consistent throughout all the disciplines here. The optics people tend to be the opposite of us. So go figure. Let's see. If you have a magnetic field, you're always going to have an X and O mode signal when you transmit through the ionosphere. And again, very easy to prove, because if you're using circularly polarized antennas, you can tell the difference between quite easily. In Fairbanks, Alaska, where we have a very large discrimination between the X and O modes, we often tune into WWV. 15 megahertz really shows that up well. And you build an HF, a circularly polarized HF receiving antenna. Very easy to do, just a turnstile antenna or a couple of couple of inverted V's at right angles to each other with a 90-degree phasing through there. And you can very typically see up to a 3 S-unit difference between being the correct circular polarization or the reverse sense. So this is not a footnote. The footnote phenomena is actually quite pronounced. So, and again, it's not going to be as pronounced if you're on the magnetic equator like Cajamarca, Peru. But if you're near the poles or anywhere where you have a lot of significant magnetic field, you're going to see a great difference in the sensitivity of an antenna, whether it's circularly polarized and counter opposite circular polarization. Very easy to demonstrate, and I without question, whenever I have somebody build a C-pole antenna for HF, they're just absolutely amazed at the difference it makes between right-left polarization. Now, as far as usefulness for amateur radio, well, this can allow us to reuse frequencies. If we're very careful about launching a circularly polarized signal, then we can very easily discriminate between right and left hand. Unfortunately, an effective circularly polarized transmitting antenna is not real handy. That's how I say it at HF. Whereas it's very easy to build an active receiving antenna that has high degree of discrimination. I wrote an article. Well, actually, I started manufacturing some of these, but I designed a thing called an hexagon antenna, which is just basically a cross-polarized active antenna, which only is about 3 feet across. And you could easily demonstrate the X and O mode predominance with radio signals. Very, very fun stuff. Let's see here. Okay, here we have another ionosphere where we actually have quite a large divergence between the X and O mode here. And again, this is in Boulder back in 2010. And you see there's just a very, very large difference in critical frequency. The X mode critical frequency about 6.5 megahertz, and it's about 5.8, 5.9 for the O mode. So in general rule, your skip distance is going to be larger with X mode. However, the absorption generally tends to be more. So you're going to have generally you're going to have weaker signals on the X mode than the O mode. Let's see. What do we have here? Yeah, okay. Let's talk a little bit more about sun here. Here's some handy websites, particularly having to do with digisons and other types of ionsons here. PSK Reporter's just done an amazing thing for doing this kind of study. Whereas even if we don't have the network of digisons that we once had, PSK Reporter's filled in a lot of those gaps there. So, I assume most of us are using PSK Reporter to some degree now. And it's become such a handy tool that it's totally revolutionized radio science and makes a whole lot easier to do. Okay. Any questions so far?
Among your references, I would also add the Institute of Physical Science in Australia does a nice map updated every 15 minutes around the clock with the cumulative effect of all these ionoson readings around the world. So they give you an FOF2 map that can be very handy.
That's great. Yeah. Well, thank you for that. We'll take note of that. Okay, a little bit back to the sun here. We have space weather, and of course, me living in Fairbanks, we see auroras all the time. We had a phenomenal aurora season last few weeks here up there, so just been some very unusual shaped auroras as well. So again, the sun is the main mover, but we have a lot of local phenomena that can add a lot to that or subtract a lot to it. Generally, as a general rule, when the aurora is the most beautiful is when the radio propagation is the worst. So you got to take your pick. If you're living last year, you want pretty auroras or you want some radio. So it's always how should I say always kind of pulled between one or the other. We have various filters on the sun looking for sunspots in the chromosphere and the ionosphere. This is a hydrogen filter here where you can see some of the more deeper depths of sun through the chromosphere. Chromosphere is actually quite a bit thicker. If you actually look at the diameter of the sun that you can see with visible light, it's quite a bit larger than it is with the hydrogen light because we have the photosphere is quite a ways away from the surface of the sun. Let's see here. These are different types of filters here, and figure out what all these are. And probably need to update this site here a little bit. But there are different types of filters we have on here. This one here is probably the more common one, the hydrogen one that we see we could see the details of the coronal holes and that sort of thing, and the sunspots. If you look at sunspot very closely, it's a very complicated structure. It's not just a hole. It's got kind of like an inverted volcano, and there's a lot of activity in there. There's a black part very black part in the middle. Nobody really knows what's inside there. The edges and the penumbra of the sunspots is pretty well known, or at least observable. Whereas where it goes into the black hole in the middle of that, nobody really knows. So there's a lot of research that needs to be done on this. Another 4 filters here, and a cumulative index of ANK case phenomenon there. You can get historical data from this GRL web portal, which has, I guess, goes back to the dark ages as far as the Digison data. So we want to know what something was happening on the last sunspot cycle. You can do that here. Again, PSK Recorder, absolutely wonderful tool. We use it all the time in radio science. And the entire world seems to be peppered with PSK Reporter sites, which is absolutely phenomenal. Let's see here. Vocap is kind of embedded into a lot of propagation software. Now, what was I thinking? N7US, Tomas, who developed what's called PropLab 3, which is actually a ray tracing program, the first ray tracing program available to radio amateurs. And that's pretty amazing too, because it will actually do a ray trace in 3 dimensions in both the X and the O mode. And I think the program's around $90. I got kind of the tail end when they were still giving it out as freeware. But if you can get a copy of PropLab 3, it's an amazing propagation tool. Again, probably more interest to the scientific than just figure out the radio propagation for contesting or whatever. But all that's good. And the vocap again is kind of built into a lot of the propagation software. For example, DX Labs uses vocap for the propagation tools there. And again, all sorts of different ways you can look at that. You could look at it in three-dimensional displays or four-dimensional displays, or you can look in black and white, which just shows basically the contours of the maximum propagation, kind of like isobar maps in weather. Let's see, circuit reliability. Okay, anybody here use WinLink? Okay, well, WinLink built into it has a circuit reliability test there. So before you actually establish a WinLink connection, it'll run through and give you a circuit reliability and a circuit path loss here. And they're kind of related together, but this is very useful here if you want to predict your chances of working a certain DX station. This is one of the tools built into vocap. So again, this is, I don't want to say this is the last word on the topic. Hopefully for some of you, it's the first word, particularly with exonote propagation. If I had a hobby horse I'd like to get on with radio amateurs in general, is just to get them exploring more with exonote propagation and learning more about, how we could use that. And, you just learn a lot more about radio when you have these tools available. So anyway, we didn't have a whole lot of questions during the beginning, so we'll open up the floor for anything here. And again, this is not the last word on the topic at all. So,
All right. Well, thank you very much. Barry, what do you got?
Questions in chat. Gene wants to know, what does the vertical green dots on the upper left corner of the graph mean in slide 11?
which one?
Upper left corner, there are green dots.
Slide 11.
Slide 11.
Slide 11. Okay, let's go over slide 11. Get that here. Oh. Oh, okay, here we go. You said upper left?
Yes,
the
upper
vertical
left.
dot. Go ahead, Gene.
Yeah, upper left, right underneath the word boulder.
Oh, that's just a noise spike. That's a little bit of noise.
Oh, okay.
Yeah, we share digisons with all the other radio services there are out there. If you look at one of the digisons from like the East Coast there in Massachusetts, there are big gaps missing because they have to filter out the radio station or not interfere with the radio station. So every digison will have certain blank regions. It would be great if you have a continuous sweep across the entire frequency, but you have to play nicely with all your neighbors there.
Okay, that makes sense. Thanks a lot.
This is John. If I could ask a question.
Sure.
This may be an impression, but having moved from Georgia to Idaho, it seems that 6-meter sporadic E seems to stop frequently at the Mississippi River. Other than that's the way it is, does physics have any kind of an explanation for that?
Stand by one. What do you think of that, Terry? By the way, I'm gonna introduce my friend here. This is Dr. Terry Bullitt, who is a guru of all propagation stuff.
Yeah, I ran the Boulder Ionosphere for 20 years. Sporadic E is highly correlated with uplifts of energy from the lower atmosphere. And orographic winds over the Rocky Mountains, for example, produce upwellings of atmospheric energy that propagate up to the 100-kilometer altitudes and generate the wind shears that are a causal mechanism of the sporadic E layer. So the sporadic E is more common in thunderstorm season where you get upwellings, and it's much more common downwind of any large mountain ranges.
So we live on the wrong side of the Rockies up here in Idaho. Thank you very much.
That would be my explanation. Yep. The Boulder Sounder sees sporadic E quite a lot because it's on the downwind side of the Rocky Mountains. As Art Bell would say, east of the Rocky Mountains.
Don't go away so soon, Terry.
Okay.
Any other question for Terry? He's a real guru. So I did it by seat of my pants. He actually has the credentials.
I have a question for either of you. Back many years ago, I do contest expeditions, and we were operating from the location of the late KL7Y in Wasilla.
Oh, yeah.
I was on 40 meters with a kilowatt and a 3-element beam, listening to a PJ2 in the Caribbean calling CQ. He was like 20 over 9. I could not get an answer from him at all. It's like I wasn't even there, even with the kilowatt and the beam. It's, you know, it sounds like the classic one-way propagation. I attributed it at the time to the fact that their thunderstorm levels create huge amounts of noise, and he might simply not have been hearing too well, but he was answering other stations. Any idea what happened there?
Well, let me give you a little anecdote of what happens up here. Now, again, we're completely different, your universe, but often we will, with a high gain 20-meter antenna, you'll hear a European station coming across, and you rotate your antenna clear around the azimuth, has zero difference in the signal strength. So, okay, how can that happen? Well, it absolutely shows that what we have is circular polarization, because it's coming straight down, and your antenna has no to a circularly polarized wave, it doesn't matter what the rotation is of a linear polarized antenna. Well, why would it be coming straight down? Because the ionosphere in Fairbanks is tilted about a 65-degree angle. So you're bouncing this low angle signal off a reflecting surface. And so it launches out horizontal, but by the time it gets to you, it's coming straight down. So we see it. X and O propagation has a lot of explanations for one-way propagation. If you've lived in Alaska at all, one-way propagation is normal. The fact that you ever have two-way propagation is phenomenal in itself. So we live with one-way propagation there.
Yeah, that was my first time operating up in that area, so it was a surprise.
Yeah. It's surprising, highly disappointing if you're used to real radio someplace else.
Yeah. Now I work near the equator.
All right, Barry, you got any more?
That's all the questions we had in chat. Gene just said that he got solar smart tonight.
Okay, Dennis, you got your hand up, sir.
Oh, I sure do. First of all, Eric, this has been brilliant presentation. I really enjoyed this a lot. This is some really great material. You alluded earlier to long delay echoes, and did you say that you've done a presentation on LDEs?
Yeah, it was a while ago, and I can't even remember all I said. But let me give you and Terry may correct me on this. He always holds my feet to the fire, make sure I don't lie. But one of the things that may be, and again, this is a possible. One of the things that really satisfies me more than any other explanation for long delayed echoes is what we call let's see, ion. Let's see, what do you call the ion acoustics? Yes. So acoustic waves through the ionosphere are much faster than sound, but they're much slower than the speed of light. Very much slower, because you actually have the motion of ions. Now, an ion can collide with a next door neighbor and propagate sound just as sound does, but there's electromagnetic field accompanied to it. So imagine like having a big reverb spring up there, which is composed of a bunch of ionized particles bouncing off each other, but they're excited by electromagnetic wave. And then since that's always reciprocal, they can propagate through ion acoustic propagation and spit out the other end. Now, one thing that makes this is even more convincing is they can produce the ion acoustic waves and delayed echoes on a much shorter time scale inside plasma chambers, enclosed plasma chambers. So the only question is all the ingredients are in the ionosphere by themselves. It's just do they all occur at the same time, which is probably a very rare phenomenon. But inside a plasma chamber, I mean, it's very reliably generate these. So that's my opinion. What do you think?
Are your long delay echoes longer than round the world
Yes,
propagation?
yes.
Oh, yeah.
Okay.
Yeah.
Well, they could also be magnetospheric ducting.
Yeah, but wouldn't the losses be huge?
No,
Okay.
especially at high latitudes.
Yeah, that's one of the
That's
commonly.
the coupling into the longitudinal propagation Whistler modes,
Yeah,
essentially, that can propagate along the Earth's magnetic field for
Yeah.
very long distances with very little loss, and will bounce off the opposite hemisphere and come back to you.
Okay, well,
And
that's
those,
another.
and those can travel at fairly low speeds.
Yeah. So that's another commonly probably the equally in terms of plausibility.
Yeah, if it's not around the world, I guess.
Yeah.
Yeah, the LDEs that's something that's fascinated me since I was a kid, and always wondered about that. And
Yeah, you don't believe it, but until you hear it the first
until you
time.
hear it, yeah, and something more than a quarter of a second, which
Yeah.
I've experienced that many times, hearing my own signal, going all the way around and coming back, making a full circuit. But yeah, anything more than that, you sit there scratching your head. It's like, where did that go, and where did it come back from? I have another question for you. You did a presentation here before on HARP.
Right.
And HARP did that experiment some years ago. I want to say it was like maybe 10, 12 years ago, where they did the moon mounts down around 40 meters.
Yeah. Yep.
Do you know of any plans for that to be ever done again, something like that? Because I have a recommendation for that. If it's ever done again, that was done on a 2-second cycle.
Right.
And, looking at your Ionosphere images where you get that second reflection, a couple of us were speculating that we could have possibly heard a second reflection going Earth, Moon, Earth, Moon, Earth. If it had gone longer than the 2-second cycle time that they used. So if that ever is done again, that's got to be stretched out to a longer time, because I would wager that we'd hear a second echo.
Well, coming from the moon, of course, we're looking at a topside sounding phenomenon, which is very different from
Right.
And I was thinking, if you landed on the moon, it would be what would EME or MEM look like?
Interesting. Well, all I remember is the signals. I live in Southern California, and so not sure what I was getting direct, if it was a ground wave, but the direct waves were very loud, but a lot of times the reflections were significantly stronger.
Well, I can tell you when
much stronger.
When my helicopter's SX-100 in a dipole, when that experiment was doing, and the moon reflection was far stronger than the ground wave.
It was amazing, amazing seeing that. That was quite an experiment, and I really enjoyed seeing that and participating in it.
Well, the HARP's becoming more privatized all the time, or I should say, physicists generated rather than the military.
Yeah,
they are always looking for somebody propose experiments to it. They will occasionally make announcements, say, hey, of course you have to pay $5,000 an hour for the time. But if you got the money and you got a proposal, they are open. They're even as we speak, they are doing a campaign of some sort. I don't know exactly what it is. Nathaniel Frizzle, everybody here on Hamsci? Okay.
Yeah, we know who that is.
There's a Hamsci group. They do a lot of radio science. And
David sounds like, or Dennis sounds like you need to apply for a grant from ARDC.
Yeah, there you go.
I like that. That's great. Well, thank you, Eric.
I do know the HARP PI very well. Dr. Paul Bernhardt, formerly of the Naval Research Lab. And if you have a suggestion for a different time period for this, the next similar experiment, I can get that to him.
Super.
Yeah, I have one other quick question, if I could.
Well, thank you. I'll back off here. I'm going to mute myself.
Oh, go ahead.
Thank you very much. Appreciate it.
It's open question time right now.
Real quick question. The definition of high and medium latitudes, Those words are always used, but there's never any numbers tied to them.
That's because it's a variable number. It's defined by different regions of different physics, and that's defined by what we call the auroral oval, or the extent of the auroral zone. And the auroral precipitation zone is dynamic from minute to minute, hour to hour, based on solar activity and solar magnetic fields and Earth magnetic field interactions. So there are some days here in Wyoming where we are a high latitude station during very active magnetic periods because the aurora has moved over us and even south of us. And there's some days when Fairbanks is considered mid-latitude because it's just so magnetically quiet.
Well, that's kind of what I thought the answer was. It makes reading some of the propagation reports that you see online difficult because they'll say at high latitudes it's this and at medium latitudes it's that. But I appreciate that it changes all the time.
It's a bit like high pressure and low pressure.
You know, a thought just came up, and you know, very early on, I talked about the difficulty of moving ions around compared to electrons. But with when you have a lot of power like HARP does, you can explore some of these nonlinear phenomena. Now, one of the first things HARP did was generating ELF by means of using the nonlinearity in the ionosphere, using two high frequency radio signals. And so there's always, you know, in science, you know, if in science, a 10-degree difference in power is considered significant, an order of magnitude. If you went to your boss and asked for a 10 dB raise, they'd probably not be into that. But in science, orders of magnitude are considered meaningful. You know, that's why HARP needed to be 10 times as powerful as high pass or whatever. You know, so but one of the last things we did when high pass observatory was around, we did a collaborative experiment with HARP. It was a ramping experiment. And we find out at what power level do you actually get the nonlinear phenomenon. And somebody always thought there was some sort of magical threshold, and you either have it or you don't. Well, we did this ramping experiment, and high pass can only run at full power. They couldn't ramp it down. So I forgot what frequency, we were around 4.5 megahertz or whatever, and we were heating the ionosphere with CW. And then we had HARP doing the same thing about 300 miles south of us. And they ramped their power down from whatever a gigawatt down to a few thousand. And you're still getting the ELF signatures down when they were running a 1,000 watts, which basically says amateur power levels, you can do nonlinear phenomena. Now they're going to be a lot weaker and the signal noise ratio is going to, but there's no magic threshold below which you can't create nonlinear phenomena. And again, the nonlinear phenomena is caused by the fact you've got rapidly accelerating electrons mixed in with slower moving ions. Now, nitrogen is very weird because it's a weird shaped molecule anyway. You have all these different excitation states, and the orbit, the orbit that you have an electron around a hydrogen atom is really weird too. So you get all sorts of weird non-linear phenomena when you're actually actively exciting the ions. And that's really what HARP was all about, is you know, playing with the ions directly. Now, there's also remote coupling. Anytime you're moving the electrons, if the electrons are associated with the ions, they're going to eventually move. But if you get enough power, you can slosh some protons around too and get some very interesting stuff. So anyway, I threw that in just to give a little insight as to why we're basically, it should be called the electrosphere, but the ionosphere is the electrons have to come from somewhere, right?
Okay. Barry, what do you got in chat?
Okay, N2PQW wants to know, does the nighttime collapse of the ionosphere equate to gray line?
Well, as I mentioned earlier, it retreats from the bottom up. So, you know, the lower frequencies tend to go long. As far as the gray line is concerned, it's probably it's really no different than process. On the one side of the gray line, it's retreating. One side, it's advancing, and that's kind of our demarcation. Now we have a real hard time really exploring much with the gray line here because in the middle of the winter, there's nothing at the other end of the gray line. It's one hand clapping. You know, we should have great gray line propagation, but look at the winter, and there's nothing at the other end. So we don't get quite the the usefulness of the gray line that you would in normal places.
I have a follow-up question on that. Are you talking about what I might call the post-midnight collapse of the ionosphere? This one propagation sort of disappears post-midnight?
And to PQW, you want to come on and follow up?
I'm sorry, I didn't realize you were asking me. Hi, it's David. No, well, I was kind of thinking out loud that you were talking about the ionosphere retreating, as you said, and as obviously it's not dark, not nighttime around the world, so that's a regional shift, not globally.
Oh,
And it seemed to me that that might somehow track the same way gray line does, but not necessarily in sense of propagation, but follow the sun or the dark.
Well, there's a phenomenon we call it the post-midnight collapse, and it comes from this for this reason. During the daytime, the ionosphere is a balance of production of ions and recombination of ions, and the recombination is collision with the neutral atmosphere. At sunset, the lower layers disappear very quickly in a matter of minutes or a short number of hours, but that leaves ionization at high altitude that can persist all night, but it is recombining all the time, and it's going away just more slowly. And like I say, it's always darkest before the dawn. The density is always least before sunrise. And past midnight, the ionosphere just can't support the ionization, and it tends to disappear rather quickly.
And go ahead.
Well, again, you explained it, and I think that's what I was describing is that, and I not necessarily tied to gray line. I understand that, but you talk about post midnight, and of course that's a shifting sand as the globe rotates. So it's a regional shift, but on the backside, it's building back up again as the sun rises, right?
Yeah, and there's another. This is very complicated. There's another process called interhemispheric transport, where ionospheric plasma can move from the northern magnetic hemisphere to the southern magnetic hemisphere. So, for example, in wintertime, northern hemisphere, summer in the southern hemisphere, they have a lot more sunlight, and the plasma generated there can move all the way up through the Earth's magnetic field and back down into the opposite hemisphere. But there's only so much of that out there, and that'll sustain the ionosphere for several hours after sunset. But sooner or later, that reservoir empties. And once that reservoir empties, the ionosphere just evaporates.
Oh, okay, very good, very good. You refer to it as a reservoir. To my mind, that seems like a wave, but that's another story.
It's a conduit.
It's a conduit, sure. It's fluid in a conduit. That's what I thought. But I'm not an expert. Thank you so much for explaining.
I might also add that when it recedes on the dark side of the sun that's when you're very likely to have chordal hot propagation. We have multiple reflections off the ionosphere because it's a very elliptical, it's not a sphere around the Earth, it's a very highly elliptical layer. And you have a lot of height between looking across the dark side of the ionosphere very far away. So you get multiple hops without intervening hops on the Earth, and that's a very low loss mode there. So it just kind of skitters across the inside of the shell there.
Okay, so but on the opposite side of the Earth, wouldn't it be more normalized then? So we have
Right.
it's depending on where it is dark, right? So wonderful.
Okay, well, going over a little bit here, but this is an interesting topic, interesting discussion, and so I did not want to interfere. As long as it was people had good questions and there was all these answers going back and forth. And okay, Dennis, you got your hand up. Go again, sir.
Yeah, another thing just occurred to me that this is going back many years ago. I met a fellow at one of our conventions, Southwest Division Convention, who was doing some research on transequatorial propagation and was relating that to, I guess, what you'd call the is it not the coronal, but the auroral circle at the North and South Pole. that there were asymmetries between the two. I don't know if you know anything about any of that, or have studied anything with transequatorial, because that's another kind of not that common phenomena that occurs at VHF.
Yeah,
Like 6
transequatorial
meters.
propagation is fairly well known.
Uh-huh.
It has to do with a phenomenon we call plasma bubbles
Okay.
that happen due to particular instabilities at the Earth's magnetic equator, or plus or minus 25 degrees
Okay.
from
At
Earth's
the
magnetic
equator. Okay.
equator. And it's very similar to a thunderstorm. It's an uprising of plasma. And unlike a thunderstorm that's full of rain and clouds, these plasma bubbles are empty. They're full of plasma turbulence, but they're largely a waveguide.
Okay.
And they can easily handle VHF and even UHF ducting,
Okay.
because it's like a conductive surface with empty space in between. It's literally a waveguide.
Sounds interesting.
And the waveguide can duct VHF and UHF propagation from one hemisphere to the other over many thousands of kilometers.
Thousands of
So
kilometers.
you can listen to TV stations from Australia up in Japan or something like that.
Yeah. Well, it's here on the West Coast here in the United States. Of course, we have the duct that goes out to Hawaii. That is that's been used all the way up to 5.7 gigahertz, which is pretty phenomenal. 2,500 miles at 5.7 gigs. They've tried to do that at 10 gigahertz. I think that's a tropoduct, is what that is.
That would have to be a tropospheric duct.
It's a tropospheric duct, and that's caused by a temperature inversion, I believe.
Yep.
Okay. Yeah, interesting stuff. Again, thank you. This has been a great topic, and really have enjoyed this tonight. I look forward to coming back and looking at the
Honored to
recording.
be with you guys again.
Hope everybody here has been paying attention. There'll be a test shortly afterwards.
Yeah, I'll grade the scores.
What's your call sign, Terry?
I'm W0 ASP, Whiskey Zero Alpha Sierra Papa.
Well, I was seeing, no, I'm not seeing. I thought I saw a hand up. Are there any more questions out there?
That was applause.
Well, thank you very much.
Tiny hands, it's hard to tell it's a thumb or is it.
Now, if you notice one phenomenon about us, we're all old guys. Where are the young whippersnappers that are into this stuff?
No,
$64 million question.
us old guys have still got some curiosity left there, so. Okay.
Their cell phones.
They're on their towers right now, putting up antennas.
Okay, are there any more questions out there?
We're good in chat.
I don't see hands up. Let's, you want to jump in with a comment or anything? Marty, thank you for joining us tonight. I appreciate your, okay.
We got a hand up, Dan.
Yeah, I see that. I'm trying to, Lino, is it? Go ahead.
Yeah, this is Lino Kilo, Quebec 4, November Gulf Hotel, by the way. This is a good talk. I'm a blind hams, however, so I could not see any of the graphs images that you were putting up there. But overall, sir, this is well informative. I can't wait to hear back down the road to the recording. And I guess well, really quick, I'll give a shout out to the Blind Hams Network. They're the ones that forwarded the email about this presentation tonight. I wouldn't have known that if they wouldn't have put out the word. So thanks, RATPAC, for doing what you do on 73. Thanks.
Well, it's an honor to talk to you. I have a very close ham friend who's blind, and she's working on a general. He says, "Well, you ought to learn Morse code." And he said, "If you learn Morse code, I'll learn Braille." So we made a deal.
Okay. Well, one more shout out there because I certainly don't want to miss anybody's curiosity, questions, or comments tonight. This has been a good one. Nothing. Well, gentlemen, it's been great. I hope to have you come back on again. You have a lot to offer, and we're right here to listen to you and learn.
Well, thank you. And again, we were always looking for people interested in helping us with experiments, so the field's wide open for anyone that just wants to investigate. And again, things like reverse beacon network and all that are just amazing for doing radio science. So It is truly citizen science.
You know, maybe you ought to give a presentation just on that subject and how to go about that, and maybe drum up some interest there.
Yeah.
The various areas. I mean, this right now we got people over the world on this particular presentation, and once it's posted, it will go everywhere. So
Okay.
maybe you might consider just doing a presentation on doing that kind of stuff.
Okay, no problem.
All right. So if you don't have it, I'll send you a link on how to find a date for it. And right now we're pretty well booked up to, I think, April. Isn't that right, Marty?
Yeah, we can do that. We can do that.
Okay. All right. We'll get back with you. Thank you very, very much. We appreciate it. And with that, I want to say 73s to everybody. Great presentation. Thank you ever so much.
33s.
Thank you, and thank you all for coming.